Okay, let's get started again. Just to begin with a minor correction to what I did in the previous lecture. It was brought to my attention that I wrote that this equation should have a solution that looks something like this. Do you agree? No? What's missing? Sorry? Yep. Yeah. Okay. So, the idea is now to move on to a new topic, which gives us a different but equivalent way of looking at Lagrange's equations. Namely, variational principles and Lagrange's equations. And in particular, we'll be concerned with what is known as Hamilton's principle. Now, what we did so far was to derive Lagrange's equations from a differential principle. We considered virtual displacements of the position vector in the system, which would be in accordance with any constraints that would be present in the system. So we derived Lagrange's equations from a differential principle. Just a second. Thanks. However, there's an alternative way of deriving Lagrange's equations, namely from a global principle, an integral principle. So in this global principle, the idea is to consider small variations in the total or entire movement of the system between 2 times t1 and t2. Well, the statement movement of system between T1 and T2 might sound a bit fuzzy. So let's be a bit more specific in saying in defining what this means. So to say something about the movement of the system, I've introduced now a concept, the configuration space. So the configuration space of the system is formed by the n-axes that are given by the generalized coordinates qn. So note that small n is different from the original number of degrees of freedom, 3n, 3 for each particle, because of any possible constraints in the system. So we assume here we have k constraints. So the number of independent generalized coordinates is n, which is equal to 3n minus k. Now, the position or state of a system, of the entire system as a whole, at any given time t, is then represented as a point in this configuration space. So imagine you have an small n dimensional space spanned by these axes of the generalized coordinates, and the state of the system at any given time t is given by a point in this configuration space. So you can think of it as this configuration space gives the position and velocity of each particle in the system at a given time t, and this is represented at a point in this configuration space. So then we can say what the system's movement is. So the movement of the system can then be thought of as a curve in this configuration space, where each point represents the state of the system at any given time t. So if we just consider the simplest case possible to try to visualize this, and let's say we have just one generalized coordinate q. and we want to consider the movement of the system between two times, t1 and t2. Let's say the system starts here and ends up here. And it goes from t1 to t2 in this manner. So for just one generalized coordinate q, we can visualize this quite easily. It's just the position of the particle or the system and how this changes with time. But in general, so this, you can think of this as a generalization to when you have multiple generalized coordinates. You have n, and this can be a very large number. So then it's harder to visualize because we can have 5-dimensional space, for instance, a 5-dimensional diagram. But the principle is the same. You have some curve in this configuration space with axis time and these generalized coordinates, and the curve in this configuration space then represents how the system moves from one point in time to another point in time. So that's the idea. Okay, so we've introduced a few concepts now, and we're ready to state what is Hamilton's principle. So Hamilton's principle is basically a statement about how will the actual movement of the system be. And it says the following: the system will take a path from t1 to t2. It will evolve from t1 to t2 in such a fashion that the action, which is defined like this, I is the action. It's given as the integral from t1 to t2 of the Lagrangian and dt, so that the action takes a stationary value, or put differently, an extremal value. This is Hamilton's principle. The real movement of the system will always be such that the action I will take a stationary value. And sorry. For our purposes, we can consider Hamilton's principle as a postulate. It's sort of an axiom which we derive other properties from. So we're not going to go into how this idea sort of sprung forth or how it came about. But it can be good for you to be aware that there are actually deep connections between Hamilton's principle and some fundamental principles in quantum mechanics as well. So for our purposes, this is just a postulate. HP is Hamilton's principle. So the L here is given as T minus V, where V depends only on the position, on the generalized coordinates, position coordinates Q, if it's a conservative system. But Hamilton's principle is also valid if the Lagrangian can be written in the form T minus U, where U is a function of Q, Q dot, and T. If you can express this generalized force in terms of U. And we actually saw an example of this a couple of lectures ago for a particle moving in an electromagnetic field, where you saw that Lagrange's equations would have exactly the same form if you could express the generalized force in the system, even if it's non-conservative, by means of this velocity-dependent potential. So Hamilton's principle is actually quite general, and for the type of system that we'll be mainly concerned with, conservative systems, it holds for sure. Well, one way to express Hamilton's principle mathematically is as follows. This is just a way to say that the action has to be an extremal value. It has to have a stationary value. So the variation of I has to be 0 for the actual path that the system takes between 2 points, T1 and T2. So the variation of the action for the real path is 0. And it turns out that we can actually derive Lagrange's equations from Hamilton's principle. So this is what we'll do now. We'll use this way of mathematically expressing Hamilton's principle to derive Lagrange's equations. Now, to keep it neat and tidy and just simple to begin with, we'll assume that there's 1 degree of freedom. So there's 1 generalized coordinate Q. Okay. Assume now that this full draw line represents the actual path, the actual movement that the system will take from T1 to T2. Oh, sorry. But imagine now that we make a small displacement of this curve. We introduce a minor variation, del q. So this dotted curve now represents a small displacement compared to the real path of the system between these two times. So we can parameterize various curves which represent minor displacements compared to this real path by introducing a parameter alpha. So I can write the expression for how q evolves with time as a function of a parameter alpha, so that alpha equals 0 represents the actual path taken by the system. This is the full line. But for non-zero alpha, we see we have some deviation here, eta of t. And this eta of t can be arbitrary, but it has to be fixed in these start and end points. So the final term in this equation represents the actual displacement compared to the real path. Okay, so let's now try to analyze the action of the system. We have the action, which is now a function of the parameter alpha. And it looks like this. So this would be the action for a path between T1 and T2 for a general alpha. So we have some virtual displacement here compared to the real path of the system. If I now consider variations of this action, so I act with del on this integral, I would get this. So keep in mind here that we're not considering any variations in time. Time is uniquely defined along each step of the curve. We're only considering possible deviations in the generalized coordinates q and their derivatives q dot compared to the real path of the system. Okay. Now, the point of introducing this alpha is to be able to switch to operators. So the two operators, del and the time derivative, commute in the final term there. So we have del q dot, and these two operators commute. So you can change place, and you can see this explicitly by expressing variations in q with alpha. And this is shown in the compendium, so I'll not do this in detail because it's provided there. But if you accept this, then we have this relation where I just interchanged the order of del and the time derivative. So let me now do this on the final term over there for del I. And we have this. What I do now is that I perform a partial integration on this term. I get this. So the first term here is unchanged. This is the same. Now, if you do a partial integration, you get one term where you should evaluate this one multiplied with the integrated of this term, which is here, and you should evaluate it at the start and the end point. And then you get minus integral where you reverse the roles of these two terms. So you get the time derivative of this term multiplied with the integral of this term, which is just del q. Okay. Is there any simplification we can do with this? In particular, this term should be evaluated at T1 and T2. Any ideas?
Well, there shouldn't be any variation at the endpoints, but it doesn't really get me any further than that.
Well, you're entirely correct. There should be no variation at T1 and T2. That was one of our assumptions. So if there are no variations, what happens with this term?
It vanishes.
Yes, because you have del Q here, and del Q in T1 and T2 is 0. So because we have no variations at the endpoints, this term vanishes. And this is what we end up with. If this term is 0, we only have the first and the second term left. And they both have a constant factor here, del Q dt. And this is precisely Lagrange's equations. Now you may think, well, this is slightly different. This is a weaker statement than Lagrange's equations because we're performing an integral. We're performing an integral over time for this. So how can we say that this is 0? Well, each of these del Q's are independent. They're generalized coordinates which are independent. So each term has to be 0. And we can generalize this. We just did this for 1 degree of freedom for simplicity, but we can generalize this to multiple degrees of freedom. Like this. So if we had started out with multiple generalized coordinates, we would have obtained that result. So then we would have n equations. So you see that Hamilton's principle gives Lagrange's equations just derived via a slightly different route than what we did originally for Lagrange's equations. And whereas this is useful in order to analyze the behavior in mechanical systems, this variational principle actually has other uses, which we'll have a look at one now. So we'll adopt basically the same idea. Assume that there is a curve y it's a function of x. So assume there's the curve y, which is a function of x between 2 points, y1 and y2. And let y prime denote the derivative of y with respect to x. So note that I'm not using dot. I'm not writing y dot is equal to dy dx, because I would like to reserve dot only for time derivation. So for spatial derivation, you can use prime, and then dot for time derivation to keep the two separate. Now, let's assume that you would like, for some reason, to find the extremal value of this integral. And there may be situations where you have a reason for wanting this, and we'll get back to this. So the integral is defined as integral from x1 to x2 over this function f, which is defined on that curve. So let me write that. Okay, so if you want to find the extremal value of this integral, we should be able to use exactly the same kind of reasoning that we did when we used Hamilton's principle to derive the Lagrange equations. So we want to find the condition so that del I is equal to 0, or put differently, that this has an extremal value. So we can use exactly the same procedure as for Hamilton's principle. And using exactly the same kind of reasoning, we obtain this equation. And this is equivalent to Lagrange's equations if you just make a few replacements. If you let f go to L, y go to q, and this prime go to dot. Right? So we're just using different symbols. We're using y and x instead of q and t. And in this context, this is known as the Euler Lagrange equations. So the point is here that this equation is the condition for making that integral over there have an extremal value. In the same way as Lagrange's equations give the condition which provides a stationary value for the action. And I see time is running away, but in the next lecture we'll have a look at an example of how we can use this. But I think we'll stop here for now.